Hello everyone! So we will start this webinar entitled How to Succeed in Integrating a DC-DC Converter in a Power System. Just before starting, a few rules and guidelines about this webinar. So it will be about an hour long and there will be a question and answer. So if you have any question, you can write them on the chat and there will be dedicated time to answer it and answer them. So to introduce ourselves, I'm Maxime Lacourcelle and I'm with Pascal Plantard. Both of us are sales engineer at Tame-Power. So about the content of this webinar, first we will introduce TRONICO and Tame-Power. Tame-Power is a brand of TRONICO. Then I will present the product of Tame-Power brand. And finally, Pascal will discuss about the general principle of power electronics, and there will be a use case at the end of the webinar. So a few words about TRONICO, which is the company, and Tame-Power is a brand of TRONICO. So TRONICO is an EMS, so electronic manufacturing service, and on ODM. So we are specializing in the design and manufacturing of complex electronically system and with high added value along the whole life cycle. So we have several kind of clients and markets. So in the aerospace industry, in the defense industry, medical industry also with some important clients. And finally, thanks to Tame-Power, we have also in the energy and transport industry. So we had about 70 million turnover in 2020, and we are about 700 employees. So we are based in France, and we also have a plant in Morocco, in Tanger. So Tame-Power, we are experts in power electronics, and especially mostly in the mobility sector. So we are clients doing a fast charger, for instance, other in the mobility industry, and finally some of them are in the aeronautics market, and some in the marine industry. We had a turnover this year of 3.5 million euros, and we also benefit from the plant in Morocco, in Tanger. We delivered more than 1,000 converters since the beginning. So I will present some of our products and what we can do. So we have know-how in the power electronics and thermal expertise for cooling the converters. We have off-the-shelf product, and we can do customization for our clients. So based on generic product or start from scratch. We can counsel you and support you in the design of your system and in the implementation of the converter inside your system. Finally, we have some industrial capacity, so we are able to deliver small and medium series with both of the plant in France and in Tanger. And we have also partnership with other company, allowing us to make a higher series and benefits from their expertise in other sector. So you can see below some of our references. I will pursue, yes, with the product. So with the DC-DC converters, we have non-insulated converters. So you can see two of them. On the left of the screen, you can see the simple unit converter, and on the right of the screen, it's a double unit. So basically, it's two single units stacked together and put in parallel. It can be driven either as a book or as a bus or bidirectional. It's driven by a CAN bus. And finally, this one are non-isolated, but we will see later that we have an isolated product to come. So the previous product were liquid-cooled converter, and the one on the left of the screen is air-cooled converter. So it's a simple unit, but as I previously said, you can stack them together to increase the maximum power. And on the right of the screen, you can see a product under development, but which is coming soon, and it's a liquid-cooled isolated converter this time. So and it will be only used as a buck for now, and maybe later as a boost. We also can offer you some accessories in order to facilitate the startup of your converters and of the product. So we have a starter kit which include the HMI software of Tame-Power and a pig can probe and some power cable in order to start faster the startup and the power up of your converter, but also it will help you for troubleshooting, and it will using the starter kit you won't have to write a dedicated software in order to communicate with the converter. So for first use it will facilitate much the use of the converter. And so you can see on this picture the HMI software on the laptop, the pig probe, the can probe, sorry, and the power cable. So we can also sell some cable to you, some power cable this time for power and high current. It's on phenol connectic, and yeah, we can supply you for connector. So now Pascal will talk about power electronic and general principle.
Yes, so some words about some definition first, just to be clear and to make easy the understanding of what I will say just later. So for DC-DC converters, we speak about not about input and output, but better in terms of low side and high side. So low side is the side where the voltage is low, and high side is the side where the voltage is high. So this is allowed to make no confusion in the case of bidirectional converter, and there is a confusion between input and output in the case of bidirectional systems. The second point is related to isolation. As Maxime said, the DC-DC converters we have are non-isolated converters. So it means that, like you can see on this picture, on the left side of the picture, the 0 volt of the low side is directly connected to the 0 volt of the high side. So there is a common copper line just between these two connections on the converter. So you have to take that in account in the design of your system and in the electric architecture of your system. Next point is about the control mode. So the DC-DC converters we propose can be controlled according to several modes. So the output of the converter can be have as a voltage source or as a current source or as a power source, which is a mix between the two previous ones. So there is here a collection of all the situation, all the configurations we can have on that. So we can just screen them. Some of them are not possible or are not physically possible. In fact, this does not depend, in fact, only on the converter, but it depends on the physical laws. So the first one is the case where there is the source is a current source and the output of the converter is a voltage source. So in this case, there is no problem with the converter, but a current source on the input means that the voltage at the input will not be defined by anything. So if it is not defined, it means that there could be a danger or an extra value of the voltage at the input of the converter. So this one shall be excluded. The other one, for exactly the same reason, cannot be adopted also. The next one is the case where the source is a current source. And the input of the converter is controlled as a voltage source. So in this case, there is no problem, and the physical is respected, and the current source will bring a certain current to the converter, and the voltage will be the one that the converter will control. The Tame-Power converters can be controlled according the input or the output of the converter. So we can do that, for example, in the case of fuel cell application. You can control the converter according to the voltage input. The next one is also a current source on the source, and the current source on the input of the converter. So this one is also not allowed because two current sources cannot be connected together. The current will be undetermined in this case. The right side of this sequence is the case where the source is a voltage source. So in this case, no problem in determining what is the voltage on the input of the converter. It's the voltage of the source. The two first on the left side are the case where the output of the converter is a voltage source, and the second one is the case where the output of the converter is a current source. The second one is the main application to charge a battery. To charge a battery, you will start the conversion as a current source in most of the cases. In this case, the load is not a resistor like represented here, but in this case, it's a battery. The battery will receive current from the converter, and the end of the charge will be done by a change in the converter control mode. It will switch to voltage control mode, and in this case, the end of the charge will be done in voltage source with the converter as a voltage source. To finalize the sequence, when the source is a voltage source and the DC-DC converter wants to be also a voltage source on the input. In this case, there are two voltage sources facing one to each other, so the voltage is not determined, and the most important is that the current will be the difference of the voltage sources divided by the resistor of the wiring in between. So this is really toxic for the systems. It cannot be implemented. And the last one is the case where the source is a voltage and the input is a current, and once again this one is a load, so no problem with that. So any combination is possible in Tame-Power converter, but some of them are physically or conceptually not allowed. This is what I call a meta architecture. It is a representation of how a DC-DC converter can be used in a technical system. So here it's a drawing done according to what is done or what is observed in most of the electric vehicle. So in this case, you can resume any vehicle to a part of this general drawing. So in a vehicle, there is an energy section on the left of the screen. This energy section is done by a fuel cell, could be done by a fuel cell, by a regenerative motor, by supercaps, or by batteries. In the middle of the system, there are what I call DC lines bridge. So once again, there are DC-DC converter that could link high voltage lines in the range of 500 to 1000 volts or 250 to 500 volts to lower voltage lines like 48 volts or 12 or 24 volts. And the last, on the right side, the last part of this drawing are the loads. The loads which can be directly connected to the DC line, to the main DC line, or to some loads which needs some specific voltage. And once again, a DC-DC converter could be required to supply a specific load working in a voltage which is not one of the DC line available in the car. So many vehicle configuration can be an extract of this configuration. For example, in the case of a 400 volt electric vehicle, then I will delete and suppress all the unused devices. In this case, we can see an onboard charger on the left side, then a fuel cell, which is feeding a drive on a motor, and also a battery is connected to the high voltage line, which in this case a 400 volts line. There could be some specific loads like compressor or air conditioning systems, and there could be also direct loads on the 400 volts line. In many cases, there is a bridge, an isolated converter making the bridge between high voltage and low voltage, 12 volt in this case. And on the low voltage, there in many cases there is a battery also, and there are some loads or some specific loads which are also connected. So we can go from this general situation where you can see all the application where the DC-DC converter that we propose can be used, to a specific application that could be yours, and you can go from one to the other and find your position in this type of system if your application is an electric vehicle. I have the same representation for a charger. In most of the chargers we have seen until now, there is a connection to the grid, and there is a battery. In some cases not, but in some cases there is also a battery. There could be some loads inside the converter itself, and there is also some coupling to grid, to external, with direct connection or isolated connection. It depends on the type, on the site that you have. In the chargers, there should be also some direct connection to a 12 volt or 48 or 24 volts for a low voltage application like automats or embedded computers. We also deal with genset applications. So in this case, on the left side, there are many energy sources that could feed the system. These sources could be directly photovoltaic system or wind turbine, for example. They could, on this drawing, there is a the position of photovoltaic and wind turbine is reversed, but anyway. So the energy incoming the DC-DC converter will feed a DC line once again. In many systems we have seen there could be also a fuel cell feeding the DC line. There could be some battery, some specific load also, and some connection to external grid, which can be local or the general grid. And in some cases, there is also a low voltage section with some specific load, some device, or even a low voltage fuel cell or low voltage battery. So the way the converter are done inside allow various power capability according to the operating point of the voltage. So what you can see here is what we call the power map. The power map is a calculation of how many kilowatts the converter can transfer from the input to the output according to the low side voltage and the high side voltage. So what you can see here is that with exactly the same converter, according to the area or the operating point you are working in, the output power can be 2 or 10 or 100 kilowatt with exactly the same hardware. So when we discuss with customers about this PowerPoint, it allows the customer to choose or to trade with the constraints they have on their system regarding the choice of the battery voltage, the choice of the fuel cell voltage, or the choice of the supercap voltage. And then according to the best area for the converter and for the other components of the system, you can choose the best operating area to select the battery, to select the fuel cell, and to select at the end the DC-DC converter, or even the number of DC-DC converter you would need for your system. So in this example, in the case where the converter is supposed to work at 400 volt on the low side and 680 volt on the high side, then the power capability of this converter is 101 kilowatts. So it means that you can transfer this energy from the input to the output. So it's really this has a great impact on the constraint solving on the architecture you have. Just to illustrate this, we have an extract of a generic power map. In the first case, we have a battery system, a battery-to-battery system. So in this case, there is a low range of voltage on one direction and a high range of voltage on the output. So we can choose the first rectangle to place the operating point of the converters. In the second application, it's a fuel cell to a battery. So the fuel cell has a large voltage range for which is the difference between the max output power and the open circuit voltage. So the converter shall accept that, and the battery has a small range of voltage range. So it's the best area in this case could be in this rectangle. And the last one is a supercap bank. So in this case, the supercap will have a large voltage range. I think there is a mix between the rectangle, in fact, and there is a very large voltage range for the supercap, because the energy is in the difference between the full charged supercap and the low charge of the supercap, and the battery system, which is a narrow voltage range. So discussing according to your system, we can discuss about the best way to place the operating point, and we can help. You can do that by yourself, but also by calling one of us. We can help it in selecting the best operating area for your converter and for the other devices of your system. So the power map is what the converter can do, but to propose something and to propose some standard in our product, we had to select some voltage area and some power area in order to provide a catalog of products. So what we do is we select an area in the power map and we do a linearization of the power capability of the converter in a certain range of voltage according to the low side voltage, and supposing a high side voltage range. So in this case, we have selected a voltage range of 300 to 400 volt on the low side, 6 to 700 volt on the high side, and we have a linear evolution of the output power capability of the converter between the two extremities of this voltage range. So this kind of power chart is what you can see on the datasheet of the product on our website. And you should understand that by evaluating how many kilowatts you can transfer through the converter when you are operating between 300 and 400 volt on the low side and 600 to 700 on the high side. This shape and this power chart is exactly the same between the simple size DC-DC converter and the double size. There is just a ratio of 2 in the power capability on these two types of devices. As Maxime said, the double size converter of our catalog is just a double power unit inside, so there is twice more power in the double size. So this curve you can find in the datasheet. They come from the power map, and the power map is at the moment a table of data that we have calculated in our lab. We will propose in the future a version of product where this table will be integrated in the product. But at the moment, the product is let's say a little bit more simple, and there is just a linearization of the power map in a certain range that we have pre-selected for the catalog. So these are the collection of power charts that we have. They have been selected according to some key applications. For example, low voltage fuel cell needs a voltage range in the area of 40-50 volts to 100 or a little bit more, and this will boost the output voltage to somewhere between 250 to 380, 400. So this is why we have selected this chart on this first power chart. Then we have various position and various slopes on the power chart according to various applications. In the case, so this is for the catalog product. In the case where you would like to have an operating area outside of what we propose, you just have to call us or to connect to the website and write your figures corresponding to your application, and we can recalculate or put your figures in a specific power map and find with you the best reference in the catalog to implement your application. Then we will follow. We will forget this power chart, and we will rebuild a new power chart adapted to your application. This is not a new software for the product. This is just a parametric adjustment for the product, so that there is no need of extra qualification or extra tests to implement this kind of facility. These are the commercial reference, so it's a pre-selected area of operating domains. You can find here the single size and the double size, and you now understand why you have two values of output power which are related to the bottom and the top of the power charts, as you can see on these figures. So on the right side you have the commercial reference. The efficiency is in the range of 98%. We have in the same way we have the power map. We also have a map with all the efficiencies, which is not exactly the same than the power map. And in most of the cases we are in the range of 98, 90, 97, 8, 9%. So the efficiency is quite high on this kind of product. Do we have some time for question or no question? Okay, I just
yes, I think there are some questions.
Does it mean that DC-DC converters cannot be used outside of the chart area? So the answer is no. You can, if the catalog DC-DC converter is this one, you can in fact use the whole power map. We can find another position in this map and redo a calculation and put the selected area in another place on the map. So the answer is no. We can elaborate a new set of parameters so that you can work in another chart than the one which is proposed on the catalog. Good, so we go ahead. Some use case. One of the use case we have is the fuel cell application. So the situation is for a vehicle, for example, where there is a fuel cell feeding a battery. So the fuel cell is, let's say, a bad voltage source. The output voltage could be in the range of 100 volts in open circuit to 500 volts at max power. This fuel cell is connected to a DC-DC converter to boost the output voltage to a battery, which is in the range of 300 to 420 volts. So how to do that? The converter will work as a boost in the boost function. It is connected to the other devices through pre-charge, because as represented on that, you have internal capacitors in the DC-DC converter. So when you connect a voltage source or any source to the DC-DC converters, then there is an inrush current incoming at the very moment where you connect the source to this capacitor. So this would lead to an inrush current that could destroy your connection, your connectors, your wires, and that could also destroy some devices inside the converter. So to escape from this dangerous situation, the usage is to put a precharge. So it's a collection of one main switch and one precharged switch connected to a resistor. So the sequence is first to connect the precharged resistor just to charge the capacitor, and when the capacitor is charged completely, then you just have to switch on the main switch, and the power will go through this line directly to the DC converter. We have exactly the same situation on the other side. So when you connect the battery, if you connect directly, there is an inrush current from the battery to charge the internal capacitors. So the battery should be connected through a precharge. Many of the battery systems already include a precharge system with this switch configuration here, and that will avoid to have too high currents in the DC-DC converter. What you can see here is that there is an internal diode, and there is the 0 to 0 internal connection, which means that it's a non-isolated DC-DC converter. The internal diode is a diode related to internal schematic inside the converter. We're in a buck boost with the internal bridges, internal bridges inside. So the transistors inside have diodes, and the equivalent diode of the system is the one which is represented on this drawing. So it means that in the case where the high side has a lower voltage than the low side, then this diode will conduct without any control. So you should avoid this situation. You can check this situation because the DC-DC converter has internal voltage, current, and temperature measurement on the input and on the high side and on the low side. So it means that you can evaluate by yourself if the voltage conditions are correct before connecting anything. In terms of functional behavior, as soon as the connection is correct, the precharge is done, and the main connection is done, and then you can start the converter. So it's very simple. You just have to discuss with the converter through the CAN bus. The converter is a pure slave CAN device, so you have to tell it to wake up first. You send it some parameters, just like the slope value to increase the voltage or the current. You can give some parameters regarding the voltage range or the current ranges where you want to have some alert in case of going through this threshold. And then you can request the converter to start converting. For example, you will set up the converter as a current source and ask it to send 100 amps to the battery, and it will immediately start converting and fill the battery with 100 amps. The voltage in this case, the voltage will be the one of the battery. The battery will determine the voltage, and the converter will feed its current. So this is a very simple use case, but it's an unusual use case on which we have many applications at the moment. If you want the current to be changed, that you just have to resend a new CAN frame, requesting the converter to feed with 50 amps instead of 100, and according to the slope and the reaction time you have previously give to the converter, it will apply that and change the current from 100 to 50. In the case where you would like to use several converters because you need more power than one single unit can provide, you can connect them. This is an example where the input is 800 volts, the output is 400 volts. You need 120 kilowatt on the output. For this application, the best point or the best area in the power map gives 50 kilowatts per converter. So you would need 3 converters to assume 100 kilowatts on the output. So you can connect them in parallel as it is proposed here. In the case, the case which is represented here is the case where one converter will determine the voltage. So the top converter will determine the voltage, and the second and the third converter will add additional current just to reach 50 kilowatts. But they will have as a current source. So this is a way to connect in parallel several converters, even if you would like to have a voltage source on the output. And the output voltage is determined by the first converter, and the additional current is brought by the other converters. If you want to change the output power, then you would have to pilot through the CAN bus the converter number 2 and 3, the second and the third one, with other values of current, just to decrease the output power. And the very last one will be the first unit, on which which is determining the voltage. In fact, this one shall always determine the voltage, so it should be the last one to be modified in the case where you want to change the output power. Yes, perhaps I forgot to say some details. Yes, one thing you should have in mind is to think about the non-isolation inside the converter. This means that all the 0-volt lines are all connected together. So in such a schematic, if one 0-volt line to one converter is really longer than all the other one, that should unbalance the current in the 0-volt line and change the electrical behavior of the converter. So you should take care of the wire length and the wire resistive path on the 0-volt line to assume a stable and a balanced share of currents in between all the 0-volt lines. Some other details about how to use the DC-DC converters. The first one is regarding the voltage overlap. In some cases, on the right side of this picture, you can see the voltage range of a converter. In the case where there is an overlap between the high side voltage range and the low side voltage range, the converter, the technology we have, cannot manage this kind of situation, so there should be a voltage drop. In the case where your application doesn't allow this voltage drop, for example, on the left side, where there is a battery, we are in a battery-to-battery system, there is an overlap between the battery on the left and the battery on the right. So to assume that, we use 2 converters, so in some cases it's mandatory. And in between these 2 converters, we program an intermediate voltage, so that the first converter will always act as a boost, and the second one will always be as a buck, and then this will allow voltage conversion, a power conversion between two devices which needs an overlap in between their voltage ranges. So this is not very usual, and this is not cost-efficient solution, but if you absolutely need the converters, this is a solution to assume a voltage overlap. I think that's all. So I've been over the whole technical domain I wanted to present to you. So I'm ready for questions. So the first one: is it possible to have a pre-charge integrated into some of these products? So it's not possible in the product that we currently have, but why this situation? The first point is that a pre-charge is really application dependent. So it's very difficult to make a calculation of a generic pre-charge according to the voltage range, and the source behavior, the sequence you would like, and so on. So we decided not to do that. The second point is that in many battery systems, the pre-charge is already integrated. So this means that in this case, the pre-charge would not be required. The third point is that in many cases, the pre-charge is requested only on one side. So that would imply us to put a pre-charge on both low side and high side, when you should require to have it only on one side, and that would make extra cost for this device. And we have chosen not to implement a pre-charge inside the product. So unfortunately, we'll have to manage this function by ourselves. Next question, is it possible to have both voltage control alternatively chosen into the same DCDC? Yes, if we go back to the first, so you can swap from one control configuration to one other with just one or two can frame. You can start the battery charge in current mode and then switch to voltage mode, or you can be in current mode on the output and swap to voltage mode on the input. For example, in a fuel cell system, you can decide to charge a battery with a current source on the output of the converter on the high side, and then after that, when the battery is charged at the right value for you, swap to determine operating point on the fuel cell, which is determined by the voltage output of the fuel cell, so the input voltage of the DC-DC converter. And you can that just by changing the can frame and change on the flight the converter position. You can even change the direction, so you can swap from buck to boost just by a can frame transmission. You can do what you want. The swap between one position and the other needs in the range of 800 milliseconds, something like that. So in some cases, it's acceptable for charge system. It's acceptable to not to deliver energy to a battery in the range of 1 second. It's not a problem. So you can do that, yes. What factors limit the voltage ranges in input output? So the main factor is the components that we have inside the product. We have capacitor, we have transistor, we have diodes, which have a maximum voltage range of operation. So this is the key factors that determine the end of the voltage range. In fact, we have some capacitor with the range of 600 volts. This one are limited to in the data sheet. We limit this family of product to 450, just to have a margin between the max voltage and the capacitor capability. And for the last 950 volt voltage range, we use transistor in the range of 1700 volts. So this is the absolute limit we use. For the 700 volts high side voltage range, we use some product with 1000 or 1200 volts. So the limit is due to the component limit we use inside, plus a certain margin that we apply. Okay, so thanks for the questions are over. So thanks for hearing us, and I hope to have some news or some request through our website. Maxime and myself will be open to answer your question. You can send on call at any moment, and that would be our pleasure to answer you.